Good afternoon. My name is Javaris Hart. I am a hello. Well, good afternoon. My name is Javaris Hart. I am a chemistry major at Jackson State University, located in Jackson, Mississippi. For the past 10 weeks, I worked in the Momeni lab under Dr. Babak Momeni, and every day I worked with Sandra Daedrick, one of these graduate students. My project, the title of my project, my summer project, is Species Interaction with the Nasal Microbiota and Coexistence in well-mixed and structured environments. To begin, we need new treatment options. Today, the rise of antibiotic-resistant bacteria is continuing to become a major problem for clinicians and researchers alike. According to the CDC, since the 1970s, the rise of Staphylococcus methicillin-resistant Staphylococcus aureus bacterium has steadily risen and continues to rise today. The cause of this is believed to be the use of broad-spectrum antibiotics and the misuse of antibiotics. This is referring to antibiotics that are used for the wrong situations, such as when a bacteria, such as when a certain many situations do not cause for the use of bacteria for antibiotics. But there's no need to fear. We do have potential solutions, and one of the solutions are microbial-based therapies. Microbial-based therapies use the individual's own derived microbial communities. Some examples of these therapies are probiotics, which are administration of beneficial bacteria to the human. Prebiotics, which is the administration of compounds that induce the growth of beneficial bacteria. Narrow spectrum antibiotics, which are antibiotics that target specific pathogens, and microbial transplantation. Microbial transplantation is the transplantation of complete microbial systems to a new host, and this has been successfully used to treat severe intestinal infections, and it's commonly used when high use of antibiotics has caused the natural microbiota to be destroyed. So the overarching objective of our lab is to develop a network that uses the individual's own microbial system to inhibit the growth of pathogens. According to this diagram illustrates that the complexity of the microbial systems, as the numbers represent different species in the community, and the lines and arrows represent the interactions that occur between these different species. And as you can see, as you increase numbers of species, these interactions become very, very complex. We chose to focus on the nasal microbiota for a variety of reasons. To begin, the nasal microbiota is a very diverse community. So we know many of the species. We already have an understanding of many of the species that are derived from this area. Many species are also easily cultured in the lab, and lastly, the nasal microbiota is a reservoir for pathogens such as Staphylococcus aureus. So, to bridge the gap in knowledge to understand these systems, we use two distinct approaches. These approaches include the bottom-up approach and the top-down approach. The bottom-up approach bottom-up approach is described as you taking one-to-one simple species interactions and building upon those interactions to build a more complex community and to build a more complex system as we gain understanding of the simple interactions. The top-down approach when we use the top-down approach, we begin with the complex system and we reduce it to stable coexisting species. In my project, I use a top-down modeling approach. We isolated 10 species from a healthy human adult. These are the 10 species. Majority are from the phylum Firmicutes, and 2 species are from the phylum Actinobacterium. We tested these bacteria in 2 specific environmental conditions: well mixed, which is a liquid media, and structured, which is on solid agar. The well mixed liquid media is a liquid, and it does not allow for structure. So the species are continuously being mixed together and mixed amongst each other, and so they cannot aggregate with like species and form communities. In the structured environment with a solid agar, the species it's structured, so the species can form niches, and which allows for several different species, like species, and individuals of like species to aggregate together and protect resources from competitors. So my project my objective was to determine which environmental conditions is more conducive to the development of a stable state community. My hypothesis was a structured environment will enable more species coexistence in comparison to an environment that does not have structure. I came to this conclusion because previous research has shown us that when bacteria species and communities have structure, it allows for like individuals of the same species to aggregate around resources and cut off competition. Now, this is not achievable in a well-mixed environment because the species are always being mixed together, so they cannot aggregate with like species and form their own niche, and form their own communities. But before I get into my specific experiments, we performed a concept called an enrichment experiment. And the basics of that is that all we're doing is continue to provide nutrients in the environment to sustain the growth of individuals that are surviving our lab conditions. We're basically adding nutrients in to keep the growth going of those who are surviving and outcompeting the others. So the two experiments I ran was a well-mixed enrichment experiment and a structured enrichment experiment. For the well-mixed enrichment experiment, we did 2 daily inoculations, one in the morning and one in the evening. After the morning inoculation, we planted 6 replicates on the agar plate, and we grew those overnight. What this allowed us to do was see which species were still present in the morning inoculation before. From this we could get our data. This is at the bottom of the screen. This is an example of a plate from one of our daily inoculations. And from this we can count the colonies, and we can get an idea of which species were still present and which species were being outcompeted. The structured enrichment experiment, we followed the same premise, except we did only one daily inoculation. We still did a daily plate to see which species were still present. The only difference was we used a 6mm filter membrane, and we only did this for logistical purposes. The purpose of being able to transfer the culture to a new plate. So looking at the results, I was able to compare the growth of coexistence in a well-mixed and versus structured with Staph aureus. And what we were able to see is in a well-mixed environment, coexistence was seen, except it was only seen between 2 species: Laciniobacillus microides and Staphylococcus aureus. Laciniobacillus microides, Staphylococcus aureus. And in the structured environment, we saw coexistence of 3 species: Lacinimbacillus microides, Staphylococcus aureus, and right there, green line, Bacillus subtilis. So what this shows, so my hypothesis was correct, that coexistence would be achieved, great coexistence would be achieved in a structured environment, but coexistence was also achieved in a well-mixed environment. But when looking at the results from the replicates without Staph aureus, a greater factor was at play here. So when I looked at the replicates with a well-mixed structured versus structured, but that did not contain Staph aureus, Lacinimbacillus microides dominated completely, outcompeted all other competitors, and no species coexistence was achieved. So what this led me to conclude was that yes, a structured environment does lead to greater species coexistence, but it also depends on which species are present. Staphylococcus aureus, without Staphylococcus aureus, no species coexistence was achieved in a structured environment. So structured environment is not the only factor that plays into whether or not coexistence can be achieved. These results corroborate previous research on naturally occurring microbial communities that state spatial structure contributes to greater community diversity. It does contribute to greater species diversity, but which species are present in that environment also plays some role. So for future experiments, sequencing of the 16S gene will be performed to verify which species, that we believe were seen in the environment. And these same techniques will also be applied to additional strains to verify to be colonizers of the nasal cavity. I'd like to give special thanks to Dr. Bobak Momeni of the Momeni Lab for allowing me to come. Also especially to Sandra Dager, who work with me every day. Also like to thank you, Dr. Kenneth Birch, for inviting me here to Boston College. Without your invite, I would not have been able to experience everything I've learned everything I've learned, and I'd be up here today to overcome my fear of public speaking. You know. But these are also some continuous results. If you have any questions, I'll be glad to answer anything. Yes.
So, is the nasal environment, is it well mixed or is it structured?
Based on previous research, the nasal microbiota is a structured environment. Yes.
So, is greater species coexistence of these bacteria a benefit to the humans that they live in, or a detriment to them?
Well, it depends on what you're looking at. So Staphylococcus aureus is a pathogen that we are trying to inhibit. So greater species coexistence is a good thing in a sense. But one thing to factor in our replicates in our well-mixed replicates with Staphylococcus aureus, as the experiment continued, the percentage of colonies that were Lacinimbacillus microides, as those numbers went up, Staphylococcus aureus was going down. So Lacinimbacillus in the well-mixed environment was beginning to inhibit the Staphylococcus aureus, which is a good sign, which is something that we were happy to see. In the structure enrichment results, in the 3 replicates containing Staphylococcus aureus, we see the same thing, but we see greater coexistence. So it depends on which species are present. So we're here as the number of in the beginning, as the number of Lacinimbacillus microides increased, the number of Staphylococcus aureus began to decrease. We also saw an increase of Bacillus subtilis. The same trend can be seen in replicate 2 and replicate 3, and a very drastic drop in replicate 3. So it depends. Coexistence is good. We want to see coexistence, but we want to see coexistence, but we want to see coexistence that is inhibiting pathogens. So yes. Does that answer your question?
Yeah.
Okay.
Would antibiotic resistance prevent coexistence between the different bacteria?
Well, no, I do not believe it would, and, because the antibiotic resistance protects the pathogen from antibiotics. But but in these environments, as Laciniobacillus microides, when it outcompetes the pathogen, that has nothing to do with the antibiotics.
You mentioned that you're going to be sequencing the different colonies how are you identifying them right now though, for these experiments?
So how we're identifying them? We sequence some of these. We sequence some of these bacteria species. So we believe that we're pretty sure about what most of these are, but we're gonna sequence them. We want to sequence them again just to be positive. We don't want to say, oh yeah, we definitely know it's Bacillus subtilis, and it turns out it's something. It's Laciniobacillus microides. Now, and also we know what each colony has a certain characteristic. So we're matching them off those characteristics. But we want to sequence them again just to be positive that we have what we think we have.
Okay, thank you.
Okay, unfortunately, that's all the time we have for questions. So